Alright, so we're starting with section 2.6, and this section is about rational functions. Now, a rational function is similar to a rational number. If you remember, a rational number is a number that can be expressed as a fraction, such as 1/3, 5/6, 2. You can always express 2 as 2 over 1, so you can express it as a fraction. So any rational number is a number that can be expressed as a fraction. And when we talk about rational functions, we're talking about functions that are fractions that are made up of one polynomial over another. So rational functions are quotients of polynomial functions. This means that rational functions can be expressed as the rational function is p of x over q of x, where p and q are polynomial functions and q of x does not equal 0. Now, the domain of a rational function is a set of all real numbers except the x values that make the denominator 0. Remember, of course, if we divide by 0, we are doing something that we're not allowed to do. Therefore, we know that we can't have any x value that's going to make q of x, that polynomial on the bottom, equal to 0. So what we're going to do is we'll actually end up using that thing to find out what the domain is. Anything that makes the denominator 0 has to be excluded from the domain. You're going to start off with the domain having all real numbers, and then you're going to take out anything like we do right here that's going to make that thing 0. So we're going to start off with, if we're looking at this polynomial right here, we got x squared plus 7x plus 9 over x, and it's already factored on the bottom, x times x minus 2 times x plus 5. Any x value that's going to make any of these factors 0, well, of course, if x is 0, then we have 0 times something, which gives us 0. If x minus 2 is equal to 0, then we have x, which is some value, times 0 times something, still get 0. And the same thing with the x plus 5. If x plus 5 equals 0, then we can find the values for these over here with any of these numbers. But I just want you to understand that just because one of these factors is equal to 0, it makes the whole denominator 0. So we have to exclude when x is 0, when x minus 2 is equal to 0, or x is 2, and when x plus 5 equals 0, or when x equals negative 5. So we have to exclude those values, but we start off with all real numbers, and we just take out the things that are going to make the denominator 0. So the domain for this is a set of all real numbers except for x equals 0, x equals 2, and x equals negative 5. So see, really easy. Alright, so let's find the domain of each of these rational functions. So remember, the only thing we're looking at here is we're looking for what is going to make the denominator 0. So the domain, and I'm going to do these in interval notation just so you can see it, but first things first, what's going to make the denominator 0 here? Well, if x minus 3 equals 0, that's going to happen when x equals positive 3. So the domain for this is all real numbers except for x equals 3. Now, if we wrote that in interval notation, the domain would be from negative infinity all the way up to but not including 3, so we use parentheses, and we would pick up after 3 and go off to positive infinity. Once again, we notice our parentheses here, we're not including 3. So with the parentheses on each side and starting at 3 and ending at 3, or ending at 3 and starting at 3, we're including all the values up to but not equal to 3. So this right here is the same thing as all real numbers except x equals 3. Alright, what about this one over here? Well, we would have to actually factor this. We're going to get x plus 3 and x minus 3. When we do that, what are going to be excluded? Well, a negative 3 here and a positive 3 here. So if we wrote this thing in interval notation, it'd be a little more complicated, but not much. What's our smallest value that we're missing? we're taking out negative 3. So negative infinity up to negative 3 to positive 3, and then positive 3 to infinity. So there is our domain. We're not including the negative 3 that would make this factor 0. We're not including the positive 3 that would make this factor 0. So we're not including negative 3 here, not including positive 3 here. Other than that, all real numbers. Now, this one over here, is there any value that will make that 0? Well, remember, if you plug any number here, positive or negative, when you square it, it's going to be positive. Then you add 9 more to it, it's always going to be positive. So this one, all real numbers. So negative infinity to positive infinity is the domain. Parentheses, parentheses. The reason parentheses with infinity is because infinity is not actually a number we can actually get to. Remember, for us to get to a number and include it, that's the only time that we use the brackets on our interval notation. All right, you guys try these 3, and I'm going to I'm going to pause the video, but I want you to pause the video as well. Try these things, work them out, see what you find to be the domain, write it in interval notation, and then I'm going to turn the video back on and show you the answers. I'm going to show you the answers in 3, 2, 1. All right, so here's the answers. The only value we're excluding here with A is positive 5. So there's our interval notation for it. For B, when we factor our denominator, we're going to have x plus 5, x minus 5, so negative 5 would make this 0, positive 5 would make that 0. Those are our 2 excluded values. So our interval notation for that would be negative infinity to negative 5, union with negative 5 to 5, a union with 5 to infinity. Remember, parentheses means we're excluding negative 5, we're excluding positive 5. All right, and over here with C, because our denominator does not factor at all, until we get into imaginary numbers, we know we include all real numbers. So the domain is negative infinity to positive infinity. All right, so using arrow notation is very important because we're going to talk about approaching values from the left and from the right and what we're defining as we're going in those directions and what's happening with what values and all kinds of things like that. So if we see this, X, arrow, and A, and then there's a plus that's in the exponent position. It's not over on this side to show that it's a positive A, it's on that side. That means we're approaching it from the right side because we're approaching it from the positive side of A. Same thing with an A minus. We're approaching it from the left. We can approach infinity and approach negative infinity in the same way. So in that case, we just say x is going to increase without bound, just go farther and further and further to the right, or in this case, further and further and further to the left. Now, here's where we would actually use this. We can define what happens to this function. As x approaches 0 from the left side, our function value goes off to infinity. Here on this side, as x approaches 0 from the right side, once again, as we come closer and closer and closer to 0, what happens to our function value? Remember, f of x is just another way of saying y. So what does the y value do? It goes off to positive infinity. Now looking at these parts down here, as x approaches negative infinity, in other words, x goes off in this, our function goes off in this direction, what's happening to our y value? Well, our y value is getting closer and closer and closer to that x-axis, so f of x is approaching 0. We say approaching because it's never actually getting there. Same thing here with our infinities. F of x can never be equal to infinity. Doesn't happen. It can approach infinity, but infinity, once again, is not a number, so it's not, hey, guess what, we're equal to infinity. And the same thing here, we're approaching 0, but it's never actually going to equal 0. Now, while we can equal 0, this case will never do that. It's just getting closer and closer and closer to 0, tinier and tinier and tinier. And the same thing happens over here. As x approaches infinity, in other words, x goes off to the right side forever and ever and ever and ever and ever, then the y value is going to approach 0. Now, the definition of a vertical asymptote says the line x equals a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as x approaches a. What that says is that as we get closer and closer to an x value of a on both sides of a, is it's going to either go off to positive infinity or negative infinity on those two sides. And here's all the possible opportunities we've got here. So coming in from the right, it can go off to positive infinity or it can go off to negative infinity. Coming in from the left, it can go off to positive infinity or negative infinity. But that's the definition of a vertical asymptote. Your graph will never cross a vertical asymptote. The reason why is because at that point, if it's going off to positive infinity or negative infinity, it has to be undefined at that value of a. That's why it goes off to positive infinity or negative infinity, because it's actually getting smaller and smaller and smaller in the denominator, going to 0, and a is a value where the denominator is equal to 0. So here's all the notation that you can look at down there, and you're going to notice here we've got limit notation. That we'll talk about later. That's kind of an intro to calculus stuff, but you can kind of see where all that information comes from. And guys, this notation right here comes directly from that limit notation. So this is nothing special. But that's what the definition of vertical asymptote is. Now, to locate a vertical asymptote, if you have the function, your rational function f of x, which is equal to p of x over g of x, or q of x, and it's a rational function in which p of x and q of x have no common factors, that means you're going to factor the top, factor the bottom, cancel out any factors that are common top and bottom. You have to. And a is a 0 of q of x, the denominator, then x equals a is a vertical asymptote of the graph of f. Now guys, don't forget this part right here where you have to cancel out any common factors. Those are values where the domain does not exist, that are taken out of the domain, but it's not a vertical asymptote. We'll talk more about that in just a little bit. But you want to factor the top, factor the bottom, cancel out any common factors top and bottom, and then any factors on the that are left on the bottom that are going to make the denominator 0, then that value of a is a vertical asymptote when you solve for x. All right, so we're looking at that's very similar to what we were looking at earlier. We've got x over x squared minus 9. Well, when we go and factor this on the bottom, we're going to have x plus 3 and x minus 3. So is there any common factors here? If you cancel out the x and the x, I'm going to punch you in the soul. Remember, you can't do that. It's got to be the whole factor that cancels out. So we don't have anything that will cancel out top and bottom. So we have vertical asymptotes at every one of the values of x that are going to make this thing equal to 0. So vertical asymptotes at x equals negative 3 and positive 3. All right, over here for this one, notice the denominator is going to factor the exact same way, x plus 3, x minus 3. But here we have a common factor of x plus 3 that's going to cancel out. So we're left with 1 over x minus 3. So the only vertical asymptote we have here is that x equals positive 3. This right here, we're going to find out later, is just a hole in the graph. It's not a vertical asymptote at negative 3. All right, and then over here on this one won't factor at all on the bottom because, so there are no vertical asymptotes because there's no value of x that will make the denominator equal to 0. All right, you guys try these three, and just like we did before, I'm going to pause the video. I want you to pause the video and work these out. Write your vertical asymptotes underneath, and then come back and check your work. I'll show you the answers in 3, 2. All right, so here's the answers. The denominators here on A and B are going to factor to x plus 1, x minus 1. No common factor to cancel out here with A, so x plus 1 gives us negative 1 is a value that's going to make that equal to 0. And positive 1 is going to make x minus 1 equal to 0. So these are the two values where we're going to have vertical asymptotes. All right, with g of x here, we've got a common x minus 1 top and bottom that cancel out. So we're left with just x plus 1 on the bottom. So negative 1 is the only thing that's going to make this denominator equal to 0 that did not cancel out. So the only vertical asymptote is at x equals negative 1. All right, over here with c, on h of x, x squared plus 1 is a sum of squares. It does not factor. Therefore, there's no value that's going to make that thing equal to 0, so there are no vertical asymptotes for it. All right, so the next thing we're going to talk about are horizontal asymptotes. We just got through talking about vertical asymptotes and how we find those, how we determine where they are, and all those things. Now we're going to talk about a horizontal asymptote. Well, a horizontal asymptote is exactly what you'd think. It's similar to a vertical, except for the fact that it's horizontal. Now, it's a little bit different in the fact that, notice here, the graph can actually cross a horizontal asymptote, and I'll explain why in just a second. And it comes from the definition. Now, the definition of a horizontal asymptote says the line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b, the y value that we're talking about here is the horizontal asymptote, as x increases or decreases without bound. Now what that means is as we go to positive infinity or negative infinity. So as we get further and further away in the x direction, in the positive x direction or the negative x direction, if we have a function that is approaching a certain value for y, that y value is the horizontal asymptote. Now you're going to find, and here's the notation right here, you'll find when we talk about limits later or in calculus, whichever one, if we get to it in pre-cal, that's great. If we don't, you'll see it in calculus if you take calculus. And that's all this is. This says the limit as x approaches infinity of f of x equals b. What that means is that as we get further and further and further to the right, our function value is going to approach that value of b. It's not going to go off and grow to infinity or go off to negative infinity. It's going to approach a certain value that we can actually write down. Infinity is not really a number, it's an idea. But if we can approach a unique number, then that means that the limit exists and that there is a horizontal asymptote. And it works in both directions. All the ones here we're showing horizontal asymptotes to the right, but it also works to the left as well. So for each one of these, we've got a horizontal asymptote of b. Now, the reason that we can actually cross our horizontal asymptote with our function is the fact that, remember, this is only what the function is approaching as x gets larger and larger and larger, or smaller and smaller and smaller, or more and more and more negative. So it's not saying that the value y equals b makes this thing undefined or anything like that, like we had with vertical asymptotes. That's why we can actually cross a horizontal, but we cannot ever cross a vertical. Because a vertical asymptote, if you remember, comes from a value where that makes the function undefined. Now, locating the horizontal asymptotes are pretty easy. We're going to look at the polynomial, the rational function we've got. And so let f be the rational function given by f of x equals a sub n x to the n plus, I'm not going to read all that. But anyway, this is just one polynomial over another polynomial, the same way we've defined a rational expression, where a sub n is not equal to 0, so this leading coefficient is not 0, and b sub m is not equal to 0, so this leading coefficient is not equal to 0. So the degree of the numerator is n. The degree of the denominator is m. And we're talking about, you know, the largest power in those polynomials. That's going to give us the degree of that polynomial. So here are the three rules. And you need to remember these because these will come back if you take calculus. If the power on top is less than the power on the bottom, or the degree on the bottom, the x-axis, or y equals 0, is the horizontal asymptote of the graph of f. So if the degree on top is less than the degree on the bottom, the y-axis, or y equals 0, is the horizontal asymptote. That's one rule. You should be able to look at it and determine it. Number 2, if the degree on top is equal to the degree on the bottom, the line y equals a sub n over b sub m is the horizontal asymptote of the graph of f. So what you do there is you take the leading coefficients and you make a fraction. And when you do that, that's going to give you the y value that the horizontal asymptote is going to be. But that only occurs if the degree on top is equal to the degree on the bottom. Now, if the degree on top is greater than the degree on the bottom, then the graph has no horizontal asymptote. So if the degree on top is, like, say 4, the degree on bottom is 3, then it's not going to have a horizontal asymptote. What that means is it's going to go off to infinity or negative infinity as x gets larger and larger and larger, or more negative and more negative. So these three rules right here you need to commit to memory. You need to know those, you need to retain those, because like I said, if you take calculus, you'll use those there as well. Alright, so let's find the horizontal asymptote, if any, of the graph of each of these rational functions. So the first one, we've got 4x over 2x squared plus 1. So the degree on top is 1. The degree on bottom is 2. So what's our rule there? Well, that's going to be the first rule. If the degree on top is less than the degree on bottom, then the horizontal asymptote is going to be y equals 0. All right, number 2, we've got a degree 2 on top and a degree 2 on the bottom. This is that second rule that says if the degree on top and the degree on bottom are equal, we're going to take the leading coefficients, make a fraction out of them. So the horizontal asymptote in this case is going to be y equals 4 over 2, which reduces to just plain old 2. And then the last one over here, we have a degree 3 on top and a degree 2 on bottom. That's our last rule that says if the degree on top is greater than the degree on the bottom, then there is no horizontal asymptote. So that's all we're doing, is we're checking the degree on top versus the degree on bottom to determine whether the horizontal asymptote exists, and if it exists, what it is. All right, so I want you guys to try these three. I'm going to show you the answers in just a second, but I want you to pause the video and try these three and see if you come up with the correct answers, and then start the video back and check your answers. I'll show you the answers in 3, 2, 1. All right, here are the answers. The first one here, we've got degree on top, degree on bottom are the same, both 2, so we have a y equals 0. Sorry, no, that's right, 3. If the top and bottom are equal, we're going to make the fraction out of the coefficient, so 9 over 3 reduces to 3. Over here with part B, with g of x, we've got a degree 1 over a degree 2. If the top is less than the bottom, the horizontal asymptote's y equals 0. And then on the last one here, we got 9x to the third over 3x squared plus 1. Degree on top 3, degree on bottom 2. If the top degree is greater than the degree on the bottom, then we have no horizontal asymptote. All right, use transformations to graph a rational function. Okay, well, we've got the graph right here. This is 1 over x squared, and we're going to graph g of x, which is going to be 1 over x minus 2 quantity squared plus 1. Now, if you remember, all of our shifts and everything come between what's added or subtracted inside and what's added or subtracted outside. This plus 1 is just going to shift the entire thing up. Well, here is my horizontal asymptote. So if I shift the entire graph up, guess what's going to happen? I'm going to shift that horizontal asymptote up as well. I'm going to have a horizontal asymptote that is right there. Actually, that's not exactly right. Let me fix that. There we go. So there's my new horizontal asymptote. And what is the minus 2 going to do? Well, remember, it's inside, so it's going to shift everything to the right, opposite the way the sign would go. So our new horizontal, or vertical asymptote would be going over 1, 2. So it's going to go right down through here. So now, then we can see how our graph behaves around the horizontal and vertical asymptotes here, and we can do very similar to what it's going to do there. So let me get the, not blue, not, let me get it purple. All right, so when we graph this thing, notice that here you got a point, 1, 1. So from there I can go and put a point right there. Actually, let me get an actual pencil, so a line tool. And the same thing over on the other side, so I'm going to have that same point right here. And then you can kind of see how it's going to behave. It doesn't have to be an exact graph, but it needs to be kind of close. Have the same behavior. So that would be the shift of the graph. So all we're doing is we're shifting that graph to the right 2 and up 1. And if you shift your asymptotes, then you've got the form or the guide for what the graph needs to look like. And there's the graph of it. Notice that it's shifted over exactly where we put it. All right, so use the graph of f of x equals 1 over x to graph g of x equals 1 over x plus 2 minus 1. All right, so 1 over x is going to look very similar. Let me go ahead and sketch it real quick. You're going to have a vertical asymptote at x equals 0, and I have a horizontal asymptote at y equals 0. And where we had x squared before, that made everything positive. Well, 1 over x doesn't make everything positive. Everything that's over here in the negative is going to be down on the negative side, and everything over here on the positive is going to be on the positive side. So let me sketch that real quick. We'll have 1 over 1, and then it's going to go up. Look. That, and same thing down here. And the way I'm getting these points right here is because what happens when we put a 1 in for x? We're going to get 1 over 1, which is 1. So that's why I know that point. And what happens when we put 1 over negative 1? We're going to get negative 1. And you can kind of think through this in the same way. What happens when you go and put 2 in there for x? You're going to get 1/2, and 1/3, and 1/4. So you're going to see that thing go down like that. So if you need some points, they're real easy to plug in something simple like this. But that's going to be the rough idea of what this graph's going to look like for 1 over x. And if we do this, what's going to happen? Well, we're going to shift down 1. So let's go ahead and we'll do purple for our new asymptotes. That's going to drop this down 1. So my new horizontal asymptote is going to be right there. And I'm going to shift to the left 2 because I've got +2 inside. So that means I'm going to go 1, 2, and my vertical asymptote is going to go right down through here. Alright, so there's my new form, and you kind of just translate all this stuff to where it needs to be. So where this point was, it's going to shift down and go up 1 over 1 and be right there. Same thing here, left 1, down 1 right there. And then just figure out what the shape's going to be. It's going to be the exact same shape it was before, except I can't draw for crap. So there's the basic shape of that thing right there. Now, a strategy for graphing a rational function is pretty easy. You're going to determine, of course, you're going to do much along the lines of what we just did, using your vertical asymptote and your horizontal asymptote to get your bases, almost kind of like the form as to how it's going to behave. And then you're also going to get some other points to see where it goes. The first one here, determine whether the graph of f has symmetry. You can do that. You don't have to do that. It's not that big a deal. Find the x-intercept. That is very important. So you're going to plug in x equals 0 and find out that's 1 point right there. If it's undefined, that means that it does not cross the y-axis. So you don't have one. That's where the if there is one comes in. Number 3, you're going to find the x-intercepts, if there are any, by solving the equation p of x equals 0. P of x, notice, is the top. So when you're looking for x-intercepts, you're looking for where the function equals 0. Well, when's the function going to equal 0? Remember, if the bottom's 0, it's undefined. The only time that this thing right here is going to be equal to 0 is if the top is equal to 0 and the bottom's not. So that's where we do the p of x equals 0 and solve it, and that's going to give you any x-intercepts that you might have. There may not be any. Alright, then you're going to find any vertical asymptotes by solving the equation q of x, the denominator equals 0, finding those places where it's undefined. and then find the horizontal asymptote, if there is one, using the rule or the rules for determining the horizontal asymptote of rational functions, the degree on top, degree on bottom thing. Then you're going to plot at least one point between and beyond each x-intercept and vertical asymptote. You need to find out what's happening in between these things. And then use the information obtained previously to graph the function between and beyond the vertical asymptotes. That means you're just going to sketch what you see and what you think it's going to behave. Remember, as it goes off to a vertical asymptote, or as it approaches a vertical asymptote, it's going to go off to infinity or negative infinity. You need to know which one, so that's where those inside points come in. And you may need more than one, but that's where those come in. So let's go through this once. All right, so let's graph f of x equals 2x minus 1 over x minus 1. All right, so if we're looking for the y-intercept, we're looking for what happens when we get f of 0. Well, if we do f of 0, we're going to have 2 times 0 minus 1 over 0 minus 1. So we're going to get negative 1 over negative 1, which gives us a value of positive 1. So that's 1 point right there. All right, and that's the y-intercept. So now we're going to find the x-intercepts. Remember, that means we're going to take the numerator and set it equal to 0. So 2x minus 1 equals 0. We're going to move that over, and we're going to get x equals 1/2 when we do the math. So x equals 1/2 is where it's crossing the x-axis. That's the only place. So now we want to find our horizontal asymptotes and vertical asymptotes. We're going to find vertical asymptotes first, which means we're going to take the denominator and set it equal to 0. So x minus 1 equals 0, and this is for the vertical asymptote, and that means that x is equal to 1. All right, and then we want to find our horizontal asymptote. Remember, the horizontal asymptote, all we're looking at is the degree on top versus the degree on bottom. Degree on top is 1, degree on bottom is 1. That means we're going to do the fraction. Remember, there's an understood 1 there, so we got 2 over 1. So horizontal asymptote is y equals 2. All right, now at that point, hopefully you can kind of see what's going to happen here. Remember, we're going to approach the asymptote, the horizontal asymptote, as we get further and further away from the origin. As we get closer and closer to this vertical asymptote, it's going to go to negative infinity or positive infinity. So hopefully you can see it's headed off in this direction. So we can go ahead and add that part in. And we could go in and put a negative 1 in our function here, just to kind of see what it looks like. So if we plug in a negative 1, we're going to have negative 2 minus 1 over negative 1 minus 1. And what do we end up with there? We end up with a negative 3 on top and negative 2 on the bottom, so 3 halves. So 3 halves will be about right there. So then we can sketch this on out. So there is one branch. That's one branch of our graph. Now we have to determine what's happening over here. Don't automatically assume that it's going to be down here or that it's going to be up here. Choose some test points. So let's let x equal 2. And if we plug in 2, we're going to get 2 times 2, which is 4, minus 1, which gives us 3, over 2 minus 1, which gives us 1. So we have a value of 2 and 3. So there's a point right there. Remember, it can pass that horizontal asymptote, so you still want another point. You need to get at least 2 points in each one of the groups. So let's go ahead and do 3. If we let x equal 3, we've got 2 times 3 minus 1, which gives me 5 on top. And 3 minus 1 gives me 2 on bottom, so that's going to be 2.5. So that's going to be right there. All right, and once again, knowing what happens as we get closer and closer to that vertical asymptote, it goes off to positive infinity or negative infinity. This one looks pretty obviously going to positive infinity. And as we get further and further away from the origin, what happens? It's going to approach that horizontal asymptote. So here is most likely what this thing's going to look like. Now, guys, understand, I don't want exact graphs, but I do want graphs with enough detail that I know that you went through the work of figuring out what all the stuff was and what it all meant and all that stuff. Don't just throw something up there. You got to have the work to support what you're putting on. Even as simple as something like that, to find the points is okay, but I need to see the work that goes along with it. All right, I want you guys to pause the video and try to sketch this graph and see what you can come up with. And I'm going to do the work here, show you what the graph looks like, but I want you guys to try it by yourself and then come back and check your work. I'll show you the work, the answer in 3, 2, 1. All right, so here's the answer. Found the y-intercept, found the function when x is equal to 0. It was 3 halves. So right there, there's your y-intercept. X-intercept, took the numerator, set it equal to 0. 3x minus 3 equals 0. Move the 3 over, divide by 3, you get x equals 1. So right there. Vertical asymptote, took the denominator, set it equal to 0, and x is equal to 2. So there's my vertical asymptote. Horizontal asymptote compared to degrees. Degree 1 over degree 1, take my fraction, 3 over 1, and my horizontal asymptote was y equals 3. All right, at that point, I just needed a couple more points, so I did an f of -1. Plug in -1 in here, I get 2. So I got that point right there. I also plugged in 3 and 4 to get some points over on this side of the vertical asymptote. And when I did, I got 6 for 3, so I got the point 3.6, and the point 4, 4.5. And then that gives me the idea of how that thing's going to behave over on that side of the vertical asymptote. So you need to pick some numbers on each side of all the vertical asymptotes and outside of the vertical asymptotes as well, just to get an idea of what the thing's going to look like. Okay, so we're going to work on this one now. Let's look at graphing it. It looks a little more complicated, but it's actually not, so don't get any big problems with it. Remember, first of all, we're going to find what the y-intercept is. So we're going to find f of 0. And you're going to have a 0 on top. And 0 squared minus 4, we'll have a -4 on bottom, so we're going to have 0, 0 as the y-intercept. So that's one point we've got there. And then we'll also find the x-intercepts by taking the numerator and setting it equal to 0. Well, 3x squared equals 0. And when we go to find the x-intercepts, you'll notice that once again we're going to set the top equal to 0, and we're just going to get x equals 0. So that's the same point we have here. Now you can have more than one. That's not going to always be the only x-intercept. You could have other x-intercepts through here as well, but that is going to be the only y-intercept. There's only going to be one y-intercept because these are functions, and remember, if you have 2 y values for any given x value, it's not a function. All right, so once we find those two, we need to find out what the asymptotes are. So to find the vertical asymptote, we're going to take the denominator and set it equal to 0. So x squared minus 4 equals 0, and we're going to have x equals 2 and x equals negative 2. So when we do that, then we know that we're going to have our vertical asymptotes at negative 2 and positive 2. We got one right. Oh, that's not what I want to do. Got one right here, and you got one over here at positive 2. All right, and then we can check for our horizontal asymptote. And remember, that's just the comparison of the degrees. Well, the degree on top is 2, the degree on bottom is 2, so we're going to take and we're going to make that fraction 3 over 1 as our horizontal asymptote. So y equals 3 is our horizontal asymptote. We go up and we put our dashed line there. Now you're going to notice this time we've got 3 different sections that we split into because of our 2 vertical asymptotes. And we need to determine where all this stuff is going to go, where our graphs are going to go. And if you notice, we've only got one point that we actually know is on the graph, and that's the point at the origin here. So we're going to have to choose some values to find out where they go. So we're going to want to go and we're going to want to choose, I'm going to do f of negative 4, f of negative 3, don't want to do f of negative 2, f of negative 1, and f of 1, and f of 3 and f of 4. And we'll do those somewhere else. So let's go ahead and do these. We've got 3 times negative 4 squared. Well, negative 4 squared is 16. 3 times 16 gives us 48 on top. And on bottom, we're going to have 16 minus 4, which is 12. So that's going to give us 4. So we have the point negative 4, 4. So that gets us that point right there. And like I said, the only point we already know is this point at the origin. All right, when we do in negative 3, we're going to have 3 times 9, which is 27 on top. And then on the bottom, we're going to have 9 minus 4, which gives us 5. 5 will go into 27 5 times. And we're going to have 2 left over, so 5 2/5. And you just estimate that. You're going to go up 1, 2, 3, 4, 5, and then roughly about 2/5. So about right there. Just a little bit under a half. That's all you got to worry about. And that'll give us an idea where as we get closer and closer to this vertical asymptote, remember it's going to take off to infinity. And as we get closer and closer to this horizontal asymptote, it's going to generally flatten out and approach that value. So when we do f of negative 1, when we plug in negative 1 here, we're going to get 3 times negative 1 squared, which is just 3, over negative 1 squared, which is 1, minus 4, which gives me negative 3. So that's going to give me negative 1. So I have negative 1, this point right here. If I plug in 1, I'm going to get 1 squared times 3, which is going to be 3 on top. 1 squared, which is 1, minus 4, gives me negative 3 on bottom again. So it's negative 1. So 1, negative 1. So what this indicates, and this is the reason why I did one on both sides of the 1 point I had. Don't assume that this thing is going to do anything in particular. In this case, it's going to almost do a parabolic thing, like a parabola, opening down. But it's not always going to. You're going to sometimes see these that will do this, and then they'll go up like this. So that's why you need different points. You need more than one point in there to make sure you know exactly what's going on. All right, so now let's go ahead and do the f of positive 3 and f of positive 4. And, well, what do you know about the x squared and the x squared? Well, remember, whatever you plug in, whether it's going to be a positive 3 or a negative 3, you're going to get the exact same answers. So this is where the symmetry comes in that we talked about. I kind of passed by it, but you can actually see here, because the x squared and x squared, you're going to have symmetry. So this point right here is going to have a matching point right here. This point right here is going to have a matching point right here. And those two branches are going to be mirror images reflected across the line x equals 0, the y-axis. So we don't actually have to find those, but we spot those because I actually spotted it right here. I didn't make note of it until right there, where a -1 gets me a -1 and a +1 also gets me a -1. That's showing symmetry right there. All right, so let's look at this one. We're going to find the f of 0, the y-intercept. That's going to give me 0 on top and 1 on bottom, so you got 0, 0 again. And to find the x-intercepts, you're going to take the top and set it equal to 0. X to the 4th equals 0 is just going to give you x equals 0. So that's going to be the same point. Like I said, it's not always going to be, but that would always be one of them if it's at the origin. All right, vertical asymptotes. We're going to look and find out when the denominator is going to be equal to 0. Well, no matter what we plug in here, so we're going to take, and when we square x, whatever x we put in there, it's going to be positive. If we have a positive number, even if it was 0, we're going to add 1 to it. So this is never, ever, ever going to be 0. So there are no vertical asymptotes. All right, and then at the same time, we need to check the horizontal asymptotes. And the horizontal asymptotes, we're using our 3 rules. And the top degree is greater than the bottom degree, so it's not going to have any horizontal asymptotes. So at that point, we know we've got this point right here, and all we need to do is grab some points and plug them in and find some values. So for instance, f of -1, f of 1, and that's just checking symmetry there. We'll see if it's symmetric. If it is, we only have to do half the work. All right, so if we plug in -1, -1 to the 4th power is going to be 1. And then -1 squared plus 1 is going to give me 2. So we've got -1, 1/2. Now if we plug in 1, guess what? 1 to the 4th power is still 1. And 1 squared plus 1 is still going to be 2. So we do have symmetry here. And it's y-axis symmetry. So once we know that, we can just plug in f of 2 and f of 3, and that's also going to give us the y values for -2 and -3. So if we plug in 2, 2 to the 4th power is going to give you 16, and 2 squared is going to be 4, plus 1 is going to give you 5. So that's going to give you 3 and 1/5. So at 2, we're going to go up 1, 2, 3, and 1/5. And we have a matching point over here due to the symmetry. And if we plug in 3, 3 to the 4th power is going to be 81. And then 3 squared is 9, plus 1 gives you 10. So that's going to give you 8.1. So at 3, we're up here at 8.1. And over here at -3, we're the same. So we're looking at a parabola-shaped thing that's just going to grow a little faster than a normal parabola. So sometimes those pieces of information don't give you anything really to go with. They don't help you out much. All right, now we can also have what's called a slant asymptote, and it's a special case. It's a special case where the degree on the top is greater than the degree on the denominator by 1 unit. So in this case right here, we've got x squared plus 1 on top, so a degree 2 on top and a degree 1 on bottom. If the top is 1 degree greater than the degree on bottom, you have what's called a slant asymptote. Now remember, if the degree on top is greater than the degree on bottom with horizontal asymptotes, we don't have one. So we don't have one, but we do have the slant asymptote. And what you do is you're going to end up taking and dividing the bottom into the top. So if I were to divide that by either long division or synthetic, I'm going to do it with synthetic. Remember, you change the sign when you put it in here. You're going to get 1 for your x squared, 0 for your x, and 1 for your constant. So we're going to bring down the 1. 1 times 1 gives me 1. Add that, you're going to get 1. 1 times 1 gives me 1. It doesn't matter if this thing does not end up with if it ends up with a remainder that's not 0. You're going to ignore that anyway. And this equation right here that you get, x plus 1, that is your slant asymptote. So when you divide it, whatever your quotient is, in other words, the answer to your division problem, that's going to be your slant asymptote. And remember, we're just dealing with y equals x plus 1. And if you look, I'm going to graph that right over here. Remember, you've got plus 1 right there. And we've got a slope of 1. So there is your asymptote right there. That's your slant asymptote. It's not exactly where it needs to be and with a slope it needs to be, but that gives you an idea. And you can notice how it's going to behave around these things. Notice that it approaches it from this side, and as it goes off to infinity, it approaches it from that side. Like I said, the line's not exactly right, but that's the idea. That's probably closer, and you can see a little better how it's going to approach it as it goes off to infinity and off to negative infinity in the two different directions. But that's how you find what the slant asymptote is. You're just going to divide what's on bottom into what's on top, and you'll have a linear expression. And the reason why you know it's going to be linear is because you got a degree 2 on top divided by a degree 1 on the bottom. When you divide that, you're automatically guaranteed to have a degree 1 result. Alright, so let's find the slant asymptote of f of x equals x squared minus 4x minus 5 over x minus 3. Alright, so when we do that, I'm going to do this one long division style, just because I did the last one in slant, or in synthetic. And when we do this, we're going to say, what do we multiply times x to get x squared? Of course, that's going to be x. X times x gives you x squared. X times negative 3 gives you negative 3x. Parentheses and subtract. X squared minus x squared goes away. Negative 4x minus a negative 3x. Remember, that's like adding a 3x. So you're going to end up with a negative x there. And then minus 5. What do you multiply times x to get negative x? Well, that's minus 1. So negative 1 times x gives you negative x. Negative 1 times negative 3 gives you a plus 3. Parentheses and subtract. Negative x minus a negative x. That's the same thing as adding, so the x's goes away. 5 minus a 3 gives you negative 8. Remember, we're going to ignore our remainder, and this is all we're looking for. So the slant asymptote, so the slant asymptote is y equals this thing right here, x minus 1. All right, you guys try this one. I'm going to show you the answer in just a second, but I want you guys to pause the video and try it. You can do it using synthetic, or you can do it using long division, but your answer should come up to be the same both ways. And I'll show you the answer so you to check it in 3, 2, 1. All right, so here's the answer, and I worked them out both ways just so you can see and you can check any errors you might have if you missed it. Here it is doing synthetic. Remember, if you're dividing by x minus 2, you want to solve that 0. So you get x equals positive 2. That's what goes in the box. And when you divide out, you're going to get 2x minus 1, remainder of 5 that we ignore. So the slant asymptote is y equals 2x minus 1. Over here, doing long division, we get the exact same thing. Remainder of 5, 2x minus 1 is a quotient, and slant asymptote is 2x minus 1, both ways. That's all for 2-6.